In this lecture, we'll look at more uses of group by, including grouping the result of joins and some details on use of non-grouping columns. We'll also introduce a more convenient syntax for joining tables, and we'll introduce the having clause. So starting right off with this new join syntax, SQL allows an alternate syntax for specifying a join and the primary key equal foreign key rule that constrains it. We'll use Bakery 3 to illustrate this alternate syntax. Instead of writing, for instance, select receipt ID price from line item product where ID equal product ID and price less than 1.0, sort of thing we have been doing, and getting this result, we can write the following. Select receipt ID price from line item join product on ID equal product ID, and then where price is less than 1.0. and get exactly the same result, as you can see. Now, this is formally called explicit join syntax, but we'll informally just call it join on syntax. The comma-separated list of joined tables is replaced by a series of table A join table B on foreign key equal primary key patterns. There's another example here. This is a join on syntax for 4 tables, and it looks like this. So we're doing select last name and price from customer C, join receipt R on CID equals customer ID, join line item on RID equals receipt ID, join product on PID equals product ID, and then finally where price is less than 1.0. All the FK equal PK clauses that were jammed together with AND clauses in the where are now right next to the join to which they apply, so they're easy to remember. Any other condition, like price is less than 1.0, in our example here, remains in the where clause. The join on syntax naturally flows from one table to the next with primary key equal foreign key clauses gluing each pair of tables together. Join on, or explicit join syntax, is generally preferred because it makes it much harder to forget the primary key equals foreign key clauses, and then also because it allows qualifications on the join keyword, saying things like left join, for instance. So you can specify different types of join, and there are several different types, as we'll see in upcoming lectures. Once you get used to it, you'll probably prefer join on to the table list syntax that we've been using up till now. But knowing both forms is important. You'll see both used in practice, and both have their advocates, though those who prefer table list syntax are really just mistaken. So both are covered in this class, and we introduced table list syntax first because once students learn join on syntax, it's kind of hard to get them to even try table list syntax. From now on, almost all our sample queries will use join on syntax. Please do so as well when answering in-lecture questions and doing exercises in IHS. Now you can apply group by to joins as well as single tables. There's the result of that, and here's the illustration of group by. For instance, say I want to get the totals for each receipt ID in the line item table from Bakery 3, listing each receipt ID and a total of all prices for all line items having that receipt ID. I can't get the product prices without joining to the product table. So we need a select receipt ID and the sum of price from line item join product on ID equal product ID, and then group by receipt ID. This query forms joined rows combining each line item with its corresponding product, and then groups by receipt ID, grouping all rows for a given receipt into a single aggregate row, including a sum of all the product prices. So question 1. Write and test a query to report first and last name of each customer along with a total cost of all their purchases in the database. List the aggregate rows that you get in that query in descending order of total purchases. You'll need to group on a 4-table join to do this. And here's what you should come up with. Select first name, last name, sum price from customer, join receipt on customer ID equal customer ID, join line item, join product, group by customer ID, order by sum of price in descending order. If we run this, we will get the desired listing. Looks like Rupert Esposito is the big spender. Now, like the prior query, this one builds a set of joined rows and then groups the joined rows by customer ID to get one aggregate row for each customer. So, wait a minute here. Customer ID is a primary key. Does it make sense to group by a primary key? Won't each primary key value appear just once? It's a slightly trick question, but it does make, well, it makes no sense to group the rows of a single table by primary key. You'd get just one row per group. But if we're grouping a join, a constrained Cartesian product, then the same primary key value may appear in multiple joined rows. And so it does make sense to group by a primary key. Yeah, let's talk a bit about selecting non-grouping columns. Note that the most recent query here doesn't even use the grouping column customer ID in the select clause. But it does select non-grouping columns, first name and last name. Does that make sense? Should the aggregate row even include values for non-grouping columns? Normally, one would expect non-grouping columns to have different values in each grouped row. For instance, say I wrote something like select flavor kind from product and group by flavor. Now, in this case, each aggregate row would have one flavor, but the common flavor rows that were grouped to create the aggregate row might have had several different kind values. Which value should be chosen for the aggregate row? It's kind of hard to say. So perhaps it's reasonable to forbid any use of non-grouping columns, like kind, in the results of the group by. But in the answer 2 SQL that we were looking at earlier, we are grouping on a primary key, customer ID. And all grouped rows forming a given aggregate row will have the same primary key and thus the same first name and last name. There's no ambiguity. So selecting these two non-grouping columns makes sense in that case. Now, the official SQL rule is the strict interpretation. Aggregate rows do not include non-grouping columns, and selecting non-grouping columns after the group by is forbidden. So trying to work with first name and last name after a group by customer ID operation would be forbidden, unless first name and last name were also included as grouping columns in the group by. Oracle, for instance, would give you an error for selecting first name and last name in this query. But MySQL has less than usual respect, shall we say, for SQL standards, so we can get away with selecting non-grouping columns in MySQL. And it's useful to do so when the non-grouping columns have the same value for all rows in a group, in particular if the grouping columns are a primary key. So what does MySQL do if you select a non-grouping column that is not the same across all grouped rows? It picks one grouped row at random to supply the non-grouping column value in the aggregate row, and this is not useful. So the simple rule of thumb is that you should select non-grouping columns only if they are part of a table for which the primary key is a grouping column. Even in Oracle, we could make the answer from question 1 work with a relatively simple modification. What would we need to do to get this to work in Oracle? Add at most a couple words to the query to make it work. The answer is that all we need to do is extend the group by to include first name and last name. Group by customer ID, first name, last name. This won't change the aggregate rows, but it will make first name and last name into grouping columns, and then this permits them in the select clause. Oracle's view is that if you have columns like first name and last name that are the same across all grouped rows, you should just include them in the group by clause so that you can use them without breaking the SQL standard. MySQL's view is that that's tedious, especially if there are a lot of such columns, and the more complex group by might slow things down, and standards are just a suggestion. So moving on to the having clause here, we have seen that aggregate function results can be used in an order by, but they cannot be used in the where clause, since that clause applies to the table that is pre-grouping or the pre-aggregation, while the order by is applied post-aggregation. So there's an important difference between pre and post aggregation. And instead, SQL offers a having clause, which works just like where, but applies to the aggregated rows, not the original ones. And the having clause may use aggregation function results as values. So let's improve on our prior query to list average price for each flavor of products so that it lists only products whose average is under $10. Select flavor average price from product, group by flavor having average price less than 10 in an order by average price. As you can see by running this, strawberry through truffle got dropped from the list. We can even use aggregate functions in having that do not appear in the select clause. If we want averages only for flavors that have, for instance, more than one product, we'd write select flavor and average price from product, group by flavor, having count star greater than 1, order by average price. And then the listing shows just the price for the 7 flavors for which there is more than one product. So let's shift to the Courses 2 database here now and do question 4. Write a query on the Courses 2 database that lists all departments that have an average number of units per course greater than 4. Give the department name, the average number of units in courses for that department, listed in descending order of the number of courses in the department, not the average. And again, only courses or only departments where the average units is greater than 4. You should get 3 rows with the sciences department first. Coming back from a pause there, what I got was select name and average of the number of units from department, and used some aliasing here, department D, join course C on department IDs matching, and then group by department ID. Having average number of units greater than 4, and then order by count star in descending order. Semicolon. And sciences, as we indicated, is first, and there are 3 of them. Now, you may even have both where and having clauses in the same select statement. The where clause will filter the pre-aggregated rows, and the having clause will further filter the post-aggregated rows. Here's a query as an example to list customer IDs and total dollar value of chocolate purchases for everyone who's purchased more than $10 worth of chocolate goods in the Bakery 2 database. Got all that? Here's the query. Select customer ID and the sum of prices, and then we're going to use receipt linked to line item, and then, or joined to line item, then joined to product. So receipt, line item, product join, where the flavor is chocolate. There's a where clause to limit the original joined rows to just those related to chocolate products. Group by customer ID, and then a having clause after that grouping to limit the aggregate rows to those with more than $10 in chocolate purchases. And as you can see, we get this result. Question 5. Okay, so write a query that lists first and last name for every student in the Courses 2 now database who has taken any computer science courses, along with the total units they've taken in computer science, but only if they've had more than 4 units in computer science. You may find table name aliasing helpful to keep this shorter. It requires a 6-table join, and that's if you don't assume a department ID number, and both a where and a having clause. And coming back from a pause then, we need to join across tables from person all the way to department, choosing via where clause then, down here, only classes from the computer science department, and then grouping by person ID, not by first last name, by the way, which might have duplicates we'd like to list separately, summing the number of units for each group, and finally filtering this so that only unit sums greater than 4 are included via a halving clause. And when we run that, hopefully it works. Here we go. So let's do one more for practice here. For each course of 3 units in the Courses 2 database, list the number of different sections of that course that have been taught, as long as no sections of the course at all were taught prior to April 1st, 2011. List the course department, title and number, the number of sections it was taught in, and the first date it was taught. Run and test it. You should get 2 results, one with 9 sections and the other with 15. Coming back from a pause there. This is what I had. We're going to select department name, a lot of aliasing here, department name and title, course number, and the number of rows, and a minimum of starting date, which comes from the term table, as you may recall. From course C, join department D, join section, join term. So a join of course, department, section, and term all together here. Now we're going to limit with a where clause to the number of units is 3, and we'll group by course ID, and then a final halving clause to limit the start date so that it must be greater than or equal to the specified April 1st, 2011. And that's what we get. Now, let's wrap up here with a brief look at the MySQL aggregate functions. MySQL offers a number of aggregate functions beyond the standard 5 supplied by SQL. These are worth a look and one in-lecture question. So check them out in the docs. Some of them, like bitand and bitor, are specialized for use in integer columns where individual bits are flags. A number of others are statistical functions, as you can see from the docs. The one we'll ask about, though, has to do with strings. Look over the MySQL aggregate functions, and then write a select statement against the Bakery 2 database that lists each kind of product once, along with a second column giving a string that comprises all the different flavors for that kind of product. And in the string, each flavor is repeated once, comma separated, and in sorted order within the string. Now, you should get 10 rows with flavor list strings ranging from 1 flavor to as many as 10 for tarts. So coming back from a pause there, here's what I had. Select kind, group concat, flavor, order by, flavor separator, comma, from product, group by kind. Now this query groups products by kind and selects the grouping column, kind, plus the aggregate function group concat, which produces a string of all the non-grouping flavor values from the grouped rows, in order and comma separated. And you can see the result here when we run it. The group concat function is a nicely convenient way to summarize the content of non-grouping columns as a single string column value.